This week we're going to look at Laplace transformations and how to use them to solve differential equations. So the general idea is that we have a differential equation, let's say with independent variable t, and we take the Laplace transformation of this differential equation to get an equation that's algebraic or exponential in a new domain S. And warning, I guess you don't have to get just an algebraic or exponential equation here. It could be a differential equation. Not necessarily even simpler, but maybe we'll see an example of that. And the idea is that maybe this algebraic equation could be easier to, you can more easily solve for whatever you need to solve for in this new domain. So we get a solution in this new domain. Using perhaps algebra, even partial fraction decomposition will be important. And then we take the inverse Laplace of this solution in domain S to get a solution in domain T for the original differential equation in domain T. It needs to be mentioned that the solution in domain S will be in terms of initial conditions or condition. So those would be necessary. We need to know what y is at time 0, so to speak, in domain T. That needs to be known. And maybe if you have higher order differential equations, you need to know what the derivatives are at time 0. Let's look at a simple example of the process of using Laplace transformations to solve a differential equation with an initial condition. So this is a pretty simple differential equation. We know the solution is y of t is e to the t. Okay, so the idea with Laplace transform is that we have this differential equation in domain t, and we're going to just take the Laplace transform without knowing what that is necessarily yet, of both sides of the equation, and that's going to transform this into an equation in domain S. So without explaining why, this is the Laplace transform of y prime of t is s times a new function in S, it's unknown, minus the initial condition of the original y at time 0. And that's equal to the Laplace transform of y of t is just y, a new function of s. So we'll use uppercase y for that. We have the initial condition is that y at 0 is 1. So you see how this is just algebra now if you wanted to solve for y of s. So bring all the terms that have a y in them to the left of the equation. That allows you to factor out the y of s. Bring anything else to the right hand side. So now we can divide by s minus 1. So now we have the solution in the domain S. So next we simply take the inverse Laplace. We take the inverse Laplace of both sides of this equation. And the inverse Laplace of y of s is the corresponding function in domain t. So we get y of t. And the inverse Laplace of 1 over s minus 1, you will learn, is just e to the t. So we get a solution to the differential equation with the initial value. So that's the general idea. So let's look at the definition of Laplace transform. It's going to be a transformation of a whole function of t. After we complete the Laplace transform, we should get a corresponding function, so we'll use uppercase letter for that function, f, big F, function of s. And the Laplace transform is defined as this improper integral. So we want to note that we're integrating f of t times this exponential, and the variable of integration is t, and here s is a parameter. And so in a sense, you're integrating out the t, and so what you should be left with at the end of the day is some expression that contains s. And so you get a function of s. And of course, this is an improper integral, so there are questions of whether this integral will even converge. Well, it turns out that as long as your function is big O an exponential, right? So it doesn't grow faster than some exponential function eventually, then this will converge. So f of t has to be big O EAT. So for example, your function were e to the t squared, this grows faster than a simple exponential like that. So this would not have a Laplace transform. Also notice that we're assuming that this function is defined just for positive values of t, or non-negative, because our integral is from 0 to infinity. An important property of the Laplace transform is that it's a linear operator. So if you have a bunch of functions that you're multiplying by numbers a and b and adding, say, the Laplace transform of a bunch of terms, you can just find the Laplace transform of each of the terms and take out the scalars. So it's a linear operator. And it's not hard to see why that would be, since a Laplace transform is an integral and integrals are linear operators. So the Laplace transform of a combination of two functions is defined as the integral of that combination times e to the st. But we know that we can integrate term by term, bring out constants. And so we see that Laplace transform is linear. This is just the Laplace transform of f of t, and this is just the Laplace transform of g of t. And it's also important to remember that the inverse Laplace transform is also a linear operator. You'll mostly be using a table of Laplace transforms to find the Laplace transforms of functions and inverse Laplace transforms. But it's good to be able to be familiar with Laplace transforms of some basic functions and be able to derive them via the definition of Laplace transform. Let's first look at the Laplace transforms of polynomials. And towards that end, we want to know how to find the Laplace transform of a basis for the space of polynomials. Let's start with the Laplace transform of a constant function, so f of t equals 1. So by definition, we're integrating from 0 to infinity 1 times this exponential, where s is a parameter, and we're integrating with respect to t. And it's an improper integral, so I know this is a limiting process, but informally, we find the antiderivative with respect to t, so s minus s is like the constant multiplying a variable t. And we compute the limit of the antiderivative at the upper bound. And so s is positive here. So this is a decaying exponential, so at infinity that goes to 0. And then we have e to the 0 is 1, so we're left with minus 1 over negative s. So 1 over s. Next, let's find the Laplace transform of the polynomial f of t equals t. And we'd use integration by parts to compute the integral. We get u times v minus the integral of v times du from 0 to infinity. Find the antiderivative of the remaining integral. And we have a polynomial in t times some decaying exponential. So as t goes to infinity, the decaying exponential wins out with the growing polynomial. So at the upper bound we get 0. Then minus at the lower bound t is 0, so we're left with 1 over s squared. Note that Laplace transforms are environmentally friendly. And in general, if your function of t is t to the power n, n is a natural number, then you can show inductively, by using integration by parts, that the Laplace transform of t to the n is n factorial divided by s to the power n plus 1. So note that that means that the inverse Laplace transform of n factorial divided by s to the power n plus 1 must be a function of t, namely t to the n. So now using this formula for the Laplace transform of t to the n, and the fact that the Laplace transform is linear operator, we can take the Laplace transform of any polynomial. Here's an example. Let's find the Laplace transform of this fourth degree polynomial in T. Using linearity, we can find the Laplace transform of each term in that polynomial. Using linearity again, we can bring out the constants multiplying the functions of T. Using the formula that we derived for the Laplace transform of T to the n, we get the Laplace transform of the 1, the Laplace transform of T, T cubed, T to the fourth. And we can simplify. Next, let's practice finding the inverse Laplace of a function of s. Suppose our function of s is 7 over s to the power 6. The key here is to force your function of s to look like n factorial divided by s to the power n plus 1. Let's factor the 7 aside, factor the exponent, or rewrite the exponent in the denominator as 5 plus 1. That tells you that we should have a 5 factorial in the numerator, so multiply the numerator denominator by 5 factorial, and use the linearity of the inverse Laplace transform to bring out the 7 divided by 5 factorial in front of the inverse Laplace transform. And now we see that we get that constant times t to the power 5. So the key is to use algebraic tricks to reshape your function of s to look like a function of s that, say, you can find on the Laplace table, Laplace transform table. Next, we find the Laplace transform of the simple exponential function of t. So we apply the definition, and using properties of exponentials, we combine this into a single exponential, factor out a -1 in the exponent. And here, for this improper integral to converge, we're going to have to assume that s is greater than a, so that s minus a is positive. So the negative of that is a negative. So we have a decaying exponential. Then the antiderivative is, with respect to t, is 1 over the negative of s minus a from 0 to infinity. So at the limit, so our antiderivative with respect to t from 0 to infinity, as t goes to infinity at the upper bound, our decaying exponential goes to 0, minus at the lower bound, where t is 0, we just get 1 over s minus a. And this also works if a is negative. Next, we derive the Laplace transform of a cosine and sine function. We'll use a complex trick to accomplish this so that we don't have to do integration by parts. Okay, let's consider the Laplace transform of cosine plus I times the Laplace transform of sine. Using the linearity of the Laplace transform, we can write that as the Laplace transform of cosine plus I sine. Here we employ Euler's identity, so that we get the Laplace transform of e to the iat. We use the definition of Laplace transform, properties of exponentials, and now we have integral from 0 to infinity of a complex number times t. And here we're going to have to take it on if you don't have experience with complex variables. We just assume that you can find the antiderivative of this exponential as you would before. It's 1 over the constant multiplying t times your exponential from 0 to infinity. We use properties of exponentials, and here we're going to use Euler's identity again. So at infinity, or as t goes to infinity, the two trig functions just keep oscillating between -1 and 1, but our decaying exponential will go to 0 as t goes to infinity. So at the upper bound, everything just goes to 0. Okay, and then minus at the lower bound. When t is 0, we get cosine of 0 here plus I sine of 0. Sine of 0 is 0, cosine of 1 is 1. Cosine of 0 is 1. So we just get 1 over, distribute the negative into the denominator, you get 1 over s minus ia. Now I'm just going to write that as in the standard form of a complex number. So real part plus I, imaginary part, by multiplying the top and bottom by the conjugate. In the denominator, we get s squared plus a squared. You can do the algebra and distribute and see, because I squared is negative 1, what would happen. And in the numerator, we get s plus ia. We can break that up into a real part of our complex plus I times the imaginary part. And you want to compare that to the original statement, Laplace transform of cosine plus I, and the Laplace transform of sine of at. So this means that the Laplace transform of the cosine is s divided by s squared plus a, and the Laplace transform of the sine of at must be a divided by s squared plus a squared. So our next pair of elementary functions are hyperbolic cosine and hyperbolic sine. We'll derive the formula for hyperbolic cosine, and the derivation for hyperbolic sine is analogous. Laplace transform of hyperbolic cosine. We use the fact that hyperbolic cosine is equal to a sum of exponentials, and make a note that similarly hyperbolic sine is the difference in exponentials, e to the at minus e to the minus at over 2. We break that up, and so that we can take advantage of linearity of the Laplace transform. We know the Laplace transform of e to the at and e to the minus at. And then we factor out the 1/2, combine the two remaining rational functions. We have a nice cancellation, and then we get our Laplace transform of hyperbolic cosine. And similarly, we would have a Laplace transform of hyperbolic sine. So now we're going to look at an important property of the Laplace transform of an exponential times a function of t. And that's going to amount to simply finding the Laplace transform of f of t, use s minus a wherever s would go. So it's the Laplace transform of f, but shifted over by amount a. So multiplying a function by an exponential here, taking the Laplace transform has the effect of shifting the transform of f of t by a. It's like a shift property. For example, we know the Laplace transform of t squared is 2 over s cubed. So if we take that t squared and we multiply it by our exponential e to the 4t, we're still going to get the Laplace transform of t squared, so 2 over something cubed, but instead of s, we'll write s minus 4. In a similar vein, we know that the Laplace transform of sine of 6t is 6 divided by s squared plus 6 squared. So with that in mind, if we encounter something like the inverse Laplace of 1 over, and now not just s squared plus 36, but s minus 1 squared plus 36, we recognize that as something that looks like the sine. So we try to we introduce a 6 in the numerator and introduce it out in the denominator. We use linearity of the inverse Laplace, and we recognize this is essentially the inverse Laplace being sine of 6t, but because of the shift, we know that that should get multiplied by e to the 1 times t. We're going to do another example. Here we're finding the inverse Laplace transform of a rational function, the quadratic over s plus 2 cubed. Towards that end, we'll want to rewrite our rational function as a sum of simpler rational functions, so that's partial fractions decomposition. You can take a moment to compute the a, b, and c here. So I get a is 1, b is negative 2, c is 3. And then we can use the linearity of the inverse Laplace function. We recognize the inverse Laplace of 1 over s plus 2 to be e to the negative 2t. We want to use the fact that the inverse Laplace of 1 over s squared is equal to t, except in our case we have 1 over s plus 2 squared. So that's just the Laplace transform, inverse Laplace transform of 1 over s squared, where s has been shifted over by negative 2. So the inverse Laplace of 1 over s plus 2 squared would be this exponential accounting for the shift, and then the Laplace transform of just 1 over s squared. Now the inverse Laplace of 1 over s plus 2 cubed. So we multiply the top and bottom by 2 factorial, or 2, take out the 1/2, and then we recognize that we essentially have something, the inverse Laplace of 2 over linear factor cubed would give us t squared, but because we don't have s here, but rather s shifted over by negative 2, we have to multiply by e to the negative 2t to account for that shift. So we get 3 times, and then 1/2 e to the minus 2t times t squared. So at the end of the day, we get a polynomial times this exponential. So if you're interested, we'll go ahead and derive this formula for the Laplace transform of exponential times a function. You can always skip this portion. So the Laplace transform of our exponential times function, by definition, is this integral. And then we combine the exponentials by using properties of exponentials, and we factor out a minus and a t, and then we simply lump the s minus a in the exponential into a new variable called z. And then we insist that s is greater than a because we need a decaying exponential in our integral so that our improper integral converges. So here the variable of integration is t. The parameter of convenience here is z. So the Laplace transform we write as f as a function of z. But we know that z is really s minus a. Next, we're going to derive the formula for the Laplace transform of f prime of t. That's going to be in term, the result is going to be in terms of s, obviously, and an initial value for f of t. So we need to know little f at 0. So we need to know an initial value. And for the Laplace transform of the second derivative of f of t, we note that recursively, right, the second derivative is just the first derivative of the first derivative. So recursively, we can use the same formula to get the Laplace transform of f double prime is s times the Laplace transform of f prime minus the initial condition f prime at 0. But we know the Laplace transform of f prime from previous. Distribute the s. So we get a nice formula for the Laplace transform of the second derivative of f of t. And inductively, you can then find a pattern here. So Laplace transform of the third derivative would be s cubed. The Laplace transform of f minus s squared, the initial value f at 0, minus s, the initial value of f prime at 0, minus the initial value f double prime at 0. So you catch the drift. The Laplace transform of the fourth derivative f with respect to t, you can recursively see is equal to this business. So for the Laplace transform of the nth derivative, you would need n initial values, right? One for f at 0, one for f prime, dot, 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 all the way through the nth derivative of f at 0. Okay, so now we're going to go back and go ahead and derive the formula for the Laplace transform of f prime. It's just an application of integration by parts. You can skip this part if you want. We use the definition of Laplace transform. Let u equal the exponential and dv be f prime dt. Du is the derivative of u with respect to t dt. V is the antidifferential of dv, so the antidifferential of f prime is just f. Integral is u times v minus the integral of v du from 0 to infinity. Factor out the minus s in front of the integral, and we see that we're left here with exactly the Laplace transform of f of t. Because f of t is big O some exponential e to the at, we can choose s large enough greater than a so that this decaying exponential will win out at infinity with this function which is whose magnitude is bounded by some e to the at. So in any case, this exponential at infinity, this wins out, and that goes to 0. We'll get 0 at the upper bound over here, and then minus the result at the lower bound when s is 0. And there we go. S times the Laplace transform of f of t minus f at 0, so the initial condition. Okay, so we're not finished with finding formulas for the Laplace transforms of various functions. We still need to look at a step function or Heaviside function, a delta function, a delta Dirac function. We want to know how to find the Laplace transform of t to the n times some function, maybe Laplace transform of convolutions. But I think we've learned enough Laplace transforms to be able to do some examples of solving differential equations using Laplace transforms. So let's do that. Okay, so for our example, let's consider the second order differential equation, non-homogeneous. The independent variable is t, and we have two initial conditions. So we're going to take the Laplace transform of both sides of this differential equation. We're going to use the linearity of the Laplace transform. And then we're going to use our formulas for the Laplace transform of y double prime. And instead of using big F, I'll use big Y to indicate, okay, so little y is a function of t, big Y is the function of s after we compute the Laplace transform. S times the initial condition for y at 0 minus the initial condition for y prime at 0. And we have minus 6 times the Laplace transform of y prime. And that's s times y of s minus the initial condition for y at 0. Then we have plus 9 times the Laplace transform for y, little y is big Y. And that's equal to, on the right-hand side, 2 times the Laplace transform of e to the 3t. So that's 1 over s minus 3. Now we're going to gather all the y terms, and then gather all the non-y terms. Our goal is to solve for y as a function of s. Dividing both sides by s minus 3 squared, we have that y is a function of s. And so now it's time to find the inverse Laplace of y of s. Towards that end, I see I can make these things look like some constant over s minus 3 to a power, in which case I know the inverse Laplace of that is going to be some exponential times some power of t. With a little algebraic sleight of hand, it would be nice if that numerator were s minus 3, so we can kind of make that happen by subtracting 3 and adding 3 in the numerator, so that way we're just adding 0. We can regroup and split that second fraction up into two separate fractions. So we had s minus 3 divided by s minus 3 squared. So now we can simplify. And we take to find y of t, we take the inverse Laplace of everything. And we recognize that these are inverse Laplace